Imagine you're planning a trip to a city you've never visited before. You have a map, some idea of where things are, and even an estimate of how far away each place is. But you want to reach your destination quickly and efficiently. That's where informed search comes into play. Informed search algorithms use additional information, something we call a heuristic, to make smarter decisions about which path to take. Think of a heuristic as a kind of educated guess about how close you are to your goal. It doesn't have to be perfect, but it gives the search algorithm a sense of direction. Let's begin with greedy best first search. This algorithm makes decisions based solely on the heuristic. It looks at the current location and says, which of my options gets me closest to the goal? And it picks that. The idea is to always choose the path that appears to lead most directly to the destination, based on the heuristic value. So if you're at a crossroads and one road seems shorter, greedy will take it, without caring about how far you've already traveled. It only looks ahead. To make this concrete, imagine you're in City A and want to reach City G. From A, there are several neighboring cities, and each one has an estimated straight-line distance to G. Greedy best first search chooses the city that has the smallest estimated distance to G. It's like being drawn toward the goal by a magnetic pull. The problem is, it doesn't consider whether that path is actually longer or more expensive overall. So while greedy is fast and seems smart, it can get stuck in dead ends or go in circles if the heuristic isn't well designed. Now, let's talk about a star search, often pronounced a star. This algorithm improves on greedy by considering two things: how far we've already traveled and how far we think we have left to go. It adds these two values together to make decisions. The distance already traveled is called the cost so far, often represented as g of n. The estimated distance to the goal is the heuristic, called h of n. A star combines these into a function f of n equals g of n plus h of n, and always chooses the path with the lowest f of n. So using the same example from City A to City G, a star will look at all possible next steps and consider both how much it costs to get there from A and how far it thinks it still needs to go. Then, it picks the one with the smallest total estimated cost. This makes a star both complete and optimal. It will always find the shortest path, as long as the heuristic doesn't overestimate the distance. That's an important point. If the heuristic is always equal to or less than the true remaining cost, we say it's admissible, and in that case A star is guaranteed to find the best solution. To illustrate this more clearly, imagine you're navigating a road network with tolls. Greedy might pick the road that looks shortest but has huge tolls, while a star will balance the tolls you've already paid with what it thinks the remaining tolls might be, and pick the smarter route overall. Another way to think about it is this. Greedy is like someone who just follows the signs that say shortest way to City G and keeps chasing that, even if the road turns out to be terrible. A star is like a cautious traveler who not only looks at those signs but also checks how long they've already been on the road, and whether there might be a better route that's longer now but shorter in the long run.